Okay, guys. Um, Please, again, if you are not there yet, please open your cameras. Feel free to open your microphones. Um, there's nothing to be worried about. Now, one announcement is okay, so as I said, we're going to have an extra lecture. Basically, it's a compensating lecture. So let's make it on Sunday, this coming Sunday at 10 a.m. Is there any objection by anybody for doing that? I'm going to write it down. Additional lecture Sunday 10 a.m. Usual Zoom. So this Sunday, let's see. Today's let me see. So we'll be talking about 29th of March. Now I have to admit there are two issues here. So I also want you to tell me. So one is that I am supposed to be traveling, so we're going to miss something like 4 lectures. Of course, right, this is going to be in May. Now, I do not know yet, given the uncertain situation, whether I will be traveling, whether it will be shortened. It's unknown. But right now, we are assuming that it will happen. So I'm supposed to give you extra lectures for that. Plus, as you've heard, so this is one thing. The other thing is, as you've heard, the semester is expected to be shortened, which is going to cause us a problem because I'm not sure that we will be able in the shortened semester to complete the things that needed to be completed in this course. So I'm thinking of when else we can add up extra lectures. Again, so far just to compensate for the missing lectures that due to my travel, without even saying anything about the shortening of the semester. Um, Right now, the next class is supposed to be April 12th. This is right after the Passover holiday. Right now, there are supposedly no classes because of repeated exams. I would like you to tell me if this is relevant for you, if there is anybody who is taking repeated exams, because if there is nobody that is taking repeated exams, then maybe we can simply add up the
I have
lecture.
an exam, so
Yeah, me
Yeah,
too.
me too.
I have your exam.
Okay, there was a glitch in the Zoom. I don't know why. I've got no idea what happened, but it happened. Okay, fortunately there will be not too much problem. Let me reshare again. So again, so one of you did say that you have an exam. When is your exam?
you said, not only me.
Well, I'm sure it's not only one. You know what?
Um,
What I ask you to do, send me an email, all of you, with the examination dates that you have. Okay? So let me do again share screening. Uh, Opened. Yeah.
are everyone in in the WhatsApp group?
Yeah. I'm not in a WhatsApp group, so
Yeah,
hold
I'm
on.
asking students.
Okay, so please,
So,
just a second. So please send me an email or emails, everybody that has exams, so we'll know that to make the compensating lectures after the exam, so that it will not interfere. But can you see my screen? Yes. So let me write it down. Please send me mails with dates of your exams. saf.fair@biu.ac.il. All right. Okay. Okay. With that, let's not lose any more time. We are talking about special relativity. Recap. Very briefly on what we did, right? We introduced the notion of four vectors, x mu. This is four vector of position. x0 is ct, x1 is x, x2 is y, x3 is z. I mentioned that if we're only using the special case, then we're going to use Latin indices. Only this will be xi. We introduced the metric eta mu nu, which is a matrix with two lower indices, -1, and everything else is a +1. We wrote down the interval, conserved quantity interval delta s squared as eta mu nu, delta x mu, delta x nu. With the Einstein summation convention, there is a summation. Einstein summation convention. It states that if we're seeing on the same side of an equation two indices, one is an upper and one is a lower, that means that we are summing over these indices. We call them dummy indices. We introduced the Lorentz transformation as a transformation between one coordinate system to another. Right. X mu prime is lambda mu prime nu x nu. We said that the upper index is the first index is superscript, the second index is a subscript. The order does matter. We gave a few examples. We showed about time dilation. Delta t prime is gamma dt. dt is the time as measured by a clock that is co-moving or not moving relative to the observer, and delta t prime. So this is 2 ticks of the clocks. This is, of course, a separation between 2 ticks of the clock in its own frame or in its rest frame. Then we moved on to generalize the discussion, and we define contravariant vector, or just vectors in short. Four vectors were defined as any object whose components transform as V alpha goes to V alpha prime, which is lambda alpha prime beta V beta, when the coordinates transform the same. X alpha goes to X alpha prime, which is lambda alpha prime beta X beta. We argue that the vectors belong to a single point in space-time. Again, in Euclidean space, it doesn't matter because it's a flat space, so you don't see that. But when we speak about non-Euclidean spaces, spaces which are curved, and again, the simplest way to think of it is think of the surface of the Earth as a two-dimensional sphere, right? Don't think of the Earth as being three-dimensional object. Think of just the surface of the Earth as being a two-dimensional sphere. And, you know, we are all obliged to that surface. I mean, we can move on that surface, but we can't move up and down into the surface, right? Then we can think of the tangent space to the surface. So we have a surface, which I call the manifold M, which I haven't properly defined, but I told you that a manifold in general is an object that is a space which is locally Euclidean, but globally is not, or not necessarily. And I choose a point, P, and then I put a space which is tangent to the space, to the manifold at that point P. That's called the tangent space TP. And the vectors are all in that point. So all the vectors V belong to TP. They live in TP. And they have all the properties that you're familiar with from vector spaces that you learn in linear algebra.
Raf, when you say locally Euclidean, can it be not locally Euclidean?
No. I mean, it doesn't have spikes. It's not a porcupine.
It's just continuous.
Yeah, it's continuous, and as you're getting closer and closer to a single point, right? When you're infinitesimally close to a point, then the approximation of Euclidean gets better and better.
Okay.
Right? The same as in Earth, right? If I'm looking at the classroom, I can easily mistaken it to be flat. Right? And when I getting closer to a given point, it gets increasingly closer to being flat, but of course the global properties are not. Another such manifold, you can think of a Mobius strip if you know what it is. You can think of many such objects, right? Any curved object, but we haven't really spoke about it now because we will speak about that more in length later on. Right now, we don't need that. So I don't want to get into that right now. Okay, right now, what you need to know to think of is that a manifold is a space which is locally Euclidean. Globally, it does not have to be Euclidean. And the simplest example that I have in my mind is the surface of the Earth. This is a two-dimensional space, right? In order to describe where you are on that space, you need to have two coordinates, longitude and latitude. But and locally, it's very good, right? You can say I'm going from here. I'm going like, in X direction and Y direction. You specify where you are relative to me, which is quite good when you speak about short distances. But when you speak about long distances, like from here to the US, that's a different story. There you can start seeing that this is not a Euclidean space, or you see it more easily than when you're locally around here. Okay, that's about the TP. Then we spoke about basis for vectors. I said that any 4-vector V, I can decompose it into components in a given basis. I can select many bases, many sets of vectors as bases. So I wrote down the vector A as A mu, E mu. So this is the components of A in the basis E mu, and E mu are the basis vectors. Of course, I have here a summation. Mu goes from 0 to 3. And then we've given an example of a tangent vector to a curve. So I can select a point, right? I can have a curve. I mean, one thing that I can always do in a manifold is to go along it. Take a path, I go to walk. And I can select this path I specify where I am on this path, right, by some parameter, which I call lambda. So lambda equal to 0 is here, lambda equal to 1, lambda equal to 2, lambda equal to 3, etc. Think of it that you are going on a hike in Shvil Israel, right? And you're telling your friends where you are, so he has the map of the hike, and what you need to specify is where you are. I'm in point number 1, day number 1 I'll be here, day number 2 I'll be here, day number 3 I'll be here. So this specifies exactly where you are, right? And then I can think of a tangent vector to a curve, right? So at the point, selecting a point on that curve, on the manifold, I can think of a vector that is tangent to it, right? That's one thing which I can do. And that will be simply V mu is dx mu over d lambda, which is indeed a vector, because when I'm changing the coordinates, right, at every point, I can always specify a set of coordinates, because I said that locally, this point is Euclidean, or getting closer and closer to Euclidean, so I can specify a set of coordinates, there is no problem. And then the curve simply specify a direction in that space in the regular way that you're familiar with. And the vector is just specify how these coordinates change along this curve, right? Which is a vector. Then we spoke about the transformation law of the basis vectors. Transformation law of the basis vectors. And we saw that they must go in the opposite way, right? So E nu prime is the opposite Lorentz transformation, which is by itself also Lorentz transformation, right? Because the opposite of Lorentz transformation is Lorentz transformation. So that's why I write it in the opposite notations of the indices. So it's a lambda nu prime. First one is lower and second one is upper. E mu. And of course, the inverse Lorentz transformation with the regular is related to the regular Lorentz transformation via the standard lambda delta function, lambda nu prime mu, lambda sigma prime mu is delta sigma prime nu prime, lambda nu prime mu, lambda nu prime rho is delta mu rho. And then I took that and I further generalized that. And I said I can think of objects which transform the same way as the basis vectors, as the set of basis vectors. That first explains why the name contravariant vectors, because they transform contra to the transformation law of the basis vectors. But now I can think of objects that transform the same way as the set of basis vectors. These are called covariant vectors. Transform the same way as the set of basis vectors. And they form a space by themselves, which is called the dual vector space. They belong to the dual vector space. Which is also known as the cotangent space, defined by TP star. And they are denoted with lower indexes, right? So if omega belongs to TP star, then we can think of omega as a map from a vector to the real number, which is done in a linear way. So omega AV plus BW is A omega that acts on V plus B omega that acts on W, and that belongs to r to the real. And the same if I have 2 omega and let's say eta belong to TP star, A omega plus B eta that operate on V is A omega that operate on V plus B eta that operate on V, and also that of course belong to R. And the shorten, since we write omega with lower indices, omega is omega mu theta mu, these are the basis vectors for the cotangent space, we end up that omega that operate on V is just omega mu V mu, which belongs to R. So omega, really, the cotangent space consists of all objects that are linear maps from V, from TP basically, from objects in TP, from the vector space to R. That may sound a little bit of abstract, but really you have already encountered that in the past. So I gave you 3 examples. So the first example is the row vectors and column vectors. V is V1, V whatever n. Omega is omega 1, omega n. Most likely you never bothered writing them with upper indexes and lower indexes, although you should have. And now you become familiar why you have to. And omega operating on V is just omega I Vi. The second example, which you have encountered already, is bras and cats, which you may or may not have fully understood the consequences of them. If not, then now is the time to fully understand them. And again, if I have a cat psi and a bra phi, then a bra operating on a cat is denoted as phi psi, which belongs to the complex number. But the correct way of thinking of them is phi and psi belong to the 2 different spaces, right? The space and the cotangent space. And the third example I gave you is a gradient, d phi over dx mu, theta mu is a gradient of a function. And I argued, there's nothing to argue here, right? Just follow the chain rule, and you'll see that under transformation, you have the d phi over dx mu prime is lambda mu prime nu d phi over dx nu, which is a transformation law of a covector. That means that phi belongs to the tangent space. So d phi is a covector. And another name, it's called a one form. It's the same objects, called one form. There's a whole theory of what's called P forms, which is very nice. It's associated with the notion of volumes, but right now I don't see how we're going to have any time looking at that. Okay. Questions before we move on? Don't mute yourself. I don't want to miss a question if you have any. Okay. And again, I urge those of you who did not, for any reason, open the camera, please open your camera. I don't really care about the mess you may or may not have at your back. That's really none of my business. It simply feels better to see that faces are not just some black screens. Okay, if you got that, and if you don't have questions, the general assumption I always have, right? You should know that in general, not just me. If somebody asks you, do you have any questions, and you don't say anything, that means that everything is fully clear. And when you're asked, you'll know how to solve any problem related to that easily. And then I expect all of you to get 100 in the exam. That is what it means that you're not answering if I ask you if you have any questions. So now, if you got that, generalization is quite easy. And the next step is to define tensors. So what is a tensor? We said that a dual vector, formally, it's a linear map from vectors to R. So we say a tensor of rank or type, it's two synonym words, KL. What is a tensor of type KL?
It has K vector elements and L covector elements.
Yes. But what is the formal definition?
Okay, it lives in C K plus L, right?
It's a what?
It has like K plus L complex numbers. It lives in.
No, first here we don't have any complex numbers, everything is real. But no, what is the formal definition? What would be?
A thing with K indices and L indices for vectors and covectors.
No, that's just the way that's just how I write it if I want to. But what will be the formal definition of a tensor?
Isn't it a correction between two vectors?
What do you mean correction?
So you have one state pointing in different directions. It's
No. You're off. Use only things that I said. I'm note that I'm very careful in defining things, and I'm only using things I define. I don't use in this course anything I don't define first. So only use things that I define. That were already defined.
That's sort of a function for vectors, like something like that.
You are close, but I didn't use the word function here because I haven't fully defined it. But no, it's not a function. It's a map, right? We said the dual vector is a linear map, right? The dual vector omega, right? Omega is a linear map that takes a vector and turn it into a real number.
So is a tensor a multilinear map?
Exactly. A tensor is a multilinear map. A tensor, a multilinear map from K what? Dual vectors and L vectors to R. Multilinearly means that it's linear in each component independently of the others.
what does this mean?
You will fully understand, don't worry. So from this point of view, when I speak of a scalar, right? A scalar is a what rank or what type of tensor is it?
The zero rank.
There is no zero here. There are two numbers. Scalar is a 0, 0 tensor or 0, 0 rank tensor. What is a vector? What type of tensor?
0.
What? 1, 0. 1, 0, exactly.
And the covector is going to be 0, 1?
Exactly. Covector is a 0, 1 rank tensor. Okay, you got it. If you got it, what would be the transformation law of a tensor? Transformation law of KL tensor. So first, how do I write a KL tensor? So it has K contravariant indices and L covariant indices. So I'll write it as T, right? Mu1, mu K, mu1, mu L. This is how I write a KL tensor in general. And what's the transformation law?
It's a linear mapping from KL tensors to KL
What
tensors.
is transform? That is what the tensor is doing. But if I want to transform a tensor from one coordinate system to another,
we use the Lorentz transformation for the whole rank for the tensor.
I'm not sure that I fully understood your answer. Please answer again.
We use the okay, so we use Lorentz transformation with this same number of in the cells for
Okay, yes,
one
yes.
of
Very good,
tensor.
very good, very good, very good. Excellent. So if I want to transform the vector, I write down T mu1 prime, mu K prime, mu1 prime, mu L prime, right? Every upper index I transform with a linear with the Lorentz transformation. So lambda mu1 prime mu1, lambda mu2 prime mu2. Let me have to erase that because I won't have space, right? Lambda mu k prime mu k. And then every lower index I transform with the inverse Lorentz transformation. Lambda nu1 prime, lambda nu L prime times T mu1 mu K nu1 nu L. It's very simple. Every upper index I transform with the Lorentz transformation. Every lower index I transform with the inverse Lorentz transformation. Or every upper index is being transformed like a vector. Every lower index is transformed like a covector.
But how do you chain these transformations together, different indices? Like it's one tensor?
I transform each component separately of the tensor.
So each component, like it would be some matrix or some tensor that transforms it, and it's completely like independent from each other index, and you're just multiplying them.
Yeah. I mean, this formula that I just wrote here. This is the transformation law of a tensor.
Okay.
Okay. Let's start. You've given that to the homework, so you can start doing that. Examples. So there is one tensor which you already seen. I have not called it a tensor because I didn't define a tensor, but now I can tell you that this is really a tensor. And this is a tensor of rank 0, 2. Let's be the first example. Rank 0, 2. And what tensor is that?
Over.
The metric.
A metric, right? It's called the metric tensor. The metric tensor, which I wrote down with two lower indices, eta, mu, nu, right? There are two lower indices, so that's a 0-2 rank tensor. Now, as any tensor, we said it can operate on two vectors, right? And so when I have eta operating on two vectors, v and w, this is such an, so what is that? This is eta mu nu, v mu, w nu. Right, that's the meaning of a tensor operating on two vectors. Now, this operation is a very important, so it has its own name. Do you know how we call that?
Contraction?
No.
It's an inner product.
This is the inner product. Very good. This is called the inner product. Or scalar product. And it's also been written as v dot w, which is equal to w dot v. Of course, it's a scalar. So what is it really? So minus v0 w0 plus vx wx plus vy wy. Now I write it in components, right? Plus vz wz. Right? These are the components. Of course, the v dot w equal w dot v because eta is symmetric, simple and symmetric. Now we're using the same terminology as we're used to from Euclidean spaces. Namely, if we have two vectors whose dot product vanishes, how do we call these vectors? If
Orthogonal.
yeah, VW is equal to 0, then we said that V and W are orthogonal. Well, of course, the dot product, this is a scalar, which means that it is not changed under Lorentz transformation, it's invariant. Which means, for example, that if you're taking a basis vectors which are orthogonal in one inertial frame, they will be orthogonal in any other inertial frame. Right? What is the norm of a vector?
And dot product of itself, square root
Right.
of dot product.
Well, yeah, it's the inner product of the vector with itself. V squared is eta mu nu, V mu, V nu, or V nu, V nu. Right? Because I can use the metric to lower and raise indices. Now, in Euclidean space, norm is always non-negative, right? But in Minkowski space, this can be either positive, 0, or negative, right? So, and we have names for that. So if eta mu nu, v mu, v nu, maybe smaller than 0, equal to 0, or greater than 0. Note that in Minkowski space, the norm of a vector can be 0 without the vector itself being 0. This is different than Euclidean space. Also, the norm of a vector can be negative. Again, this is different than Euclidean space. So if it's smaller than 0, it has a name, which you may know, may heard of.
It's time-like.
This is called a time-like. If it's equal to 0,
Light.
yeah, it's called either light-like or null. And if it's greater than 0,
Space-like.
or space-like, that's true. So again, it's the same terminology that we're used to. Well, the light-like, time-like, and space-like you don't. Of course, the norm of a vector is scalar. So it has to be a Lorentz invariant, which you can easily check. For example, in a different coordinate system, the primed v prime squared is eta mu prime nu prime v mu prime v nu prime. But I can use the transformation law. So eta mu prime nu prime v mu prime is lambda mu prime rho, and then v nu prime is lambda nu prime sigma v rho v sigma. But then since I can use that, this is transformation law of the metric. This is just eta rho sigma v rho v sigma, which is v squared in the unprimed frame. Okay. In fact, when you get used to it, it gets very, very easy. You're seeing one upper index, one lower index, you know you're summing over them. Right. Of course, this and that, and this one and this one. Another tensor of use is the Kronecker delta. What type of tensor or what rank of tensor this is?
A 1-1.
Yeah, this is a 1-1 tensor. And the components are very simple, right? Delta mu nu is 1 if mu is equal to nu and 0 otherwise. The third tensor of use is called the inverse metric. So how do I write it?
To 0, right?
What?
It's a to 0 tensor if the metric
Like I
is
said,
0
it's a
to
2-0 tensor, so I'll write it with two upper indices. Eta mu nu, upper indices now. This is a type 2-0 tensor. And is defined to be the inverse of the metric, namely eta mu nu, eta rho nu rho is eta rho nu eta nu mu, which is just delta mu rho. I can use the Kronecker delta to define the inverse of the metric. It's fairly easy to check that when you write it in a matrix form, it will look identical to the metric. Of course, this is only true in Cartesian coordinate systems in special relativity, flat spacetime. And the last tensor that we need for now is called the Levi-Civita tensor. This is a tensor of rank 0,4. Which is defined by epsilon mu nu rho sigma is equal to what? The Levi-Civita, I'm sure you've encountered it. Again, you may not have called it a tensor, though it really is. Actually, it is not exactly, you'll see that. But for now, actually, it is the realm of special relativity, it is a tensor. I'm not really cheating. What's the definition of the Levi-Civita tensor?
One for a cyclic.
Right. So it's either a +1 or a -1 or a 0. So one is if mu nu rho sigma is even permutation or even permutation of 0, 1, 2, 3. It's a -1 if this is odd permutation. Zero, 1, 2, 3, and it's 0 otherwise.
Yeah, so
Yeah.
I saw it written somewhere that Levi-Civita is not a tensor because it has some like
Yeah, it's not
weird
a,
cat
yeah,
thing.
that's what I said. It's not a tensor if the space-time is not flat. Right now, the space-time is flat because it's special relativity, so it's okay.
Okay.
So that's what I said. I'm not cheating. For special relativity, it is a tensor. When we go to curved spaces, which we will go to curved spaces, then you see that it's not exactly a tensor. We'll have to do something to make it a tensor.
Okay.
Right now, that's why we start with special relativity. Right now, it's perfectly okay to think of it as a tensor. Yeah? Okay. So just to make sure you're with me, what is epsilon 0321?
Zero.
What?
-1.
Yeah. So I have to make a one switch, right? So it's a minus epsilon 0312, and then I have the second switch, so it's a plus epsilon 0132, and then it's another switch, so this will be the switch that, and now I have this switch, so it's a minus epsilon 0123, so I have a -1. Right? If that confuses you, then again, I mean, I'm sure you've encountered that. I don't exactly remember, or I don't know where you encountered that, but I'm sure you have.
I've encountered it, but what do you mean by switches?
I switch the order of the indices, right? This is 0. I start from a 0, 1, 2, 3. Then I switch the order of 1 and 2. So I get 0, 3, 2, 1. Sorry, 0, 3, 1, 2. Then I switch the 1 and 3. So it's 0, 1, 2, 3. 1, 3, 2. Excuse me again. Then I switch the 3 and 2, and I get to 0, 1, 2, 3. And every such switch adds up a minus sign.
Okay.
I had to make 3 switch, 1, 2, 3. So I ended up with a minus. Okay. Manipulating tensors. I've got plenty of things to say about tensors, and we will say way more about tensors, but right now we're only doing the basics that we need. So manipulating tensors. There are several things we can do with tensors. Right now we'll do a few basic things. The first thing is raising and lowering indices. So we can use the metric and its inverse to raise and lower indices. Done using the metric only, right? The metric and its inverse. So let's say we given a tensor, T, alpha, beta, gamma, delta, right? We can use the metric and the inverse metric to define new tensors. For example, T, alpha, beta, gamma, delta. I can use it with eta, mu, gamma. And what am I going to get? I'm going to get a new tensor, T. What's going to be the first index in this new tensor?
Mu, right?
No.
Oh.
What is when I took this tensor T, right? Now I multiply it by the inverse metric eta. Right?
It's all going to be
Oh.
contravariant, no?
Gonna
You're
be what?
replacing.
It's all going to be contravariant, no?
No, not all are going to be contravariants.
So,
What will be the first? What happens to the first index? What happens to the first index?
Alpha, beta, mu, and then gamma downstairs.
Correct. Thank you. Well done. So the first index I don't touch, right? It's alpha, upper index. The second index is beta, again, not touched. The third index, which was a gamma, is a lower index. Now I multiply by eta mu gamma, so now it becomes a gamma, a mu with an upper index. And then the last index, again, I don't touch. I created a new tensor.
Why are we doing it from right to left and not left to right? Why are we doing it based off of the t t subscript and not off of the eta first?
We can do it like that. It doesn't really matter because there is summation here, right? When I write it like that, remember there is always a summation here.
Okay, so does the order matter? Can the mu be
The order
first?
matters, yes. I mean, when I do the multiplication, no, but when I write down the tensor, the order matters. Of course it does. Why I do it like that, this is just for you to make it easier for you to follow. But there is
Okay.
nothing more than that. Give you another example, right? So if I write down T alpha beta gamma delta, multiply by eta mu alpha, what am I going to get? What will be the first index?
Lower mu.
Lower mu, that's right. What is going to be the second index?
Upper beta, then lower gamma and lower delta.
Beta, exactly. Then lower gamma and lower delta.
I just want to clarify, is the inverse metric, it's in matrix form, it's written in the same way as the regular metric, correct?
Well, if you're looking about Cartesian coordinate system in flat space-time, then yes, correct. But if you're looking at, for example, even in flat space-time, if you're taking polar coordinate system, then no. The correct definition of the inverse metric is right here. It's defined such that its components, when you multiply them by the metric, gives you a delta function. So that depends on which system you're using. It's of course easiest to think of Cartesian coordinate system in flat metric, in flat space-time, so it's a minus plus plus plus. Then yes, they look exactly the same. But if you just think, you do it for yourself as an exercise, write down the metric in a polar coordinate system, or theta phi. If you want to make it easier on you, just do it in 2D or in theta, and then you write down the inverse. You see that they don't look exactly the same.
Thank you.
All right. And next, just one more example, just to make sure. Let's write it down at mu alpha, eta nu beta, eta rho gamma, eta sigma delta, T alpha beta gamma delta. What is that going to be? What's going to be the first index here? Fast, guys.
Alpha.
No.
Covariant
Wait.
alpha.
No. So
What's going to be the first index?
Mu.
Lower alpha, no?
No, because I'm summing over alpha. Alpha becomes a dummy
Ah.
index.
The lower mu.
what's that thing? Oh no, what's the thing before the gamma on the eta?
Row. This is a row, you mean?
Okay, so the row will be first.
No.
Then it'd be
No. Row is not going to be first.
It's
What's
a
going to
lower
be the first?
mu, no?
It's a lower mu, right? The first is alpha here. So I have a eta mu alpha. So the first is a lower mu.
Then lower than mu.
Lower what?
Lower nu.
Mu.
Lower nu. What's the third?
Upper the row, then
Row.
upper sigma.
Upper row and then upper sigma. Okay, very importantly, the positions of when I lower or raise indices, the position doesn't change. If alpha was the first index, right, then now mu will become the first index. They don't shift their position. Okay, when I do that, alpha now becomes a dummy index. Alpha, beta, gamma, and delta, they all become dummy indexes. Right? Now, the concrete example, and quite useful, is that we can turn vectors into covectors and vice versa, right? Using the metric and its inverse. So if I have a vector v nu, I write v mu is eta mu nu v nu. And if I have a covector, omega nu, I can turn it into a vector, omega mu, by multiplying by eta mu nu. So the metric and the inverse metric enables me to transform between vectors and covectors. Okay? This, by the way, this is exactly why, if you were wondering why the gradient, you always used to think of it as a vector, not as a covector, although it is a covector, because in 3 dimensions, right, the metric in Euclidean space, the metric and the inverse metric look exactly the same. Right? There is no time component which add up this minus sign. So it's easy to confuse because there is nothing that tells you. Of course, in 4 dimensions, this is not the same, right? In 3D, the gradient, 3D Euclidean space, I should say. In 3D Euclidean space, the Euclidean space, right? Gradient looks like a vector. That's not true in general because, right, in 4D, omega mu, of course, is a minus, omega 0, omega 1, omega 3. There's this extra minus sign. Of course, in the curved space-time, it's going to be much more pronounced. That's one thing we can do, using the metric to create new tensors by raising and lowering indices. Another thing which we can do is called contraction. Which is an operation that takes a KL tensor and turns it into a K minus 1 L minus 1 tensor by summing over 1 upper and 1 lower indices. It has to be 1 upper and 1 lower. You cannot have summing over 2 indices which are both upper or lower. So for example, right, I can contract, if I have a tensor, let's say T mu nu rho sigma nu, right? I have the same index. It appears twice, once as an upper and once as a lower, so I can simply contract. This is S mu rho sigma. I should emphasize it is only permitted to contract 1 upper and 1 lower indices.
Yeah, can we take a tensor and change one in this to make it this happen?
I'm not sure to understand your question, so please repeat it again.
Can we take a the tensor, change one of its in the says to a one that's all the there to a contract it?
Yes, we can change. We can take, like I did here, exactly what I showed here. If I have a tensor with two indices, I can contract one upper with one lower index. This is allowed. Is that the question? If so, then yes. And then we can
No, like what we did before changing in the cells with the metric. Can we use that to make to action of tensors we want to contract?
Again, we're talking about two separate operations, right? So of course we can operate first with symmetric. So let's say I have a tensor, right? T, here it's T alpha, beta, gamma, delta, right? I can use the metric to create a new tensor. So this is an operation which is independent, right? The metric and the integer to create a new tensor, and then I can take this new tensor and contract it. So I can make, but this is, I consider this to be two separate basic operations on tensors, right? So yes, I can combine them. If this is the question, yes, I can combine. I can take a tensor, use the metric to produce another tensor, and then I can make a contraction of this new tensor. Is that the question? Did I answer your question?
Thank you.
Okay, good. Just one thing to note is that again, the order of the indices matter, right? Order of indices matter. So T mu nu rho sigma nu is not the same tensor as T mu rho nu sigma nu. The order matters. These are not the same tensors. You have to be very, very careful when you're writing down all these tensors. I told you it's going to be quite confusing for you at the beginning. Okay. Also later on at the end as well. It's going to be quite confusing to you to make sure that you're writing down all these tensors, all these indices. I told you, make sure that you review your Greek. You're going to make use of a lot of Greek symbols here.
And this is true even if it could be contracted, like it can in the example?
Contraction gives you a different tensor. It's not going to be the same tensor if you're making contraction. If you're contracting, for example, here, the second index with the fifth index, and here you're contracting the third index with the fifth index, you're not going to get the same tensors. It's going to be, in general,
Okay.
two different tensors. Okay, play a little bit with that and you'll see. Okay, that's enough math for now. We'll go back for the math, but right now we just have enough math that we can do physics.
Can I ask a question?
Yes.
About the lowering and the indices?
Yes.
What happens if I take the metric and I don't apply it from the left, but from the right?
Here it doesn't matter.
It doesn't matter.
You're
So
doing
I
it.
get the same.
It's when you write it like that, it's with the indices, right? It's a term by term basically. As long as you keep the order, right? For example, right? This is easier like that, but you can write it down as v nu eta mu nu, give you the same thing. As long as you keep the order of the indices, that's fine.
So only the order of the tensor of the indices in the tensor matters.
Yes.
The order of the metric
Yes.
doesn't matter. So even if I take, for example, if I look at this example, if I take input eta nu beta and then eta mu alpha, I get the same answer.
Essentially here, yes.
Okay.
You don't care because you're doing the multiplication term by term, really.
Okay. Thank you.
Okay. think of it like we gave this example here, right here. Omega of V is omega I VI. Since you're really summing here term by term, the order of summation doesn't matter as long as you keep on doing the summation over all the terms that you have. Okay, that's just enough math for us to proceed on. So now we're going to go back to physics, and now you're going to see that now comes the really magical part. Nearly, you're going to see that all the physics that you derived about special relativity with these new mathematical tools that we just acquired, we're going to get them all for nearly for free. So we're going to do now special relativity kinematics, special relativity kinematics. So we're going to start by for velocity, acceleration, and forces. So the first thing, so what we're interested now is to describe the motion of a particle through space-time. We want to discuss the motion of a particle through space-time. Again, in classical mechanics, we're used to think of the position of the particle as a function of time, right? Xi classical. We have xi is xi of t, right? I is 1, 2, 3. Of course, this is meaningless. Not meaningless. It's not meaningless, sorry, but it's not very useful because t is the dimension itself, right? It can vary itself. So the best is to consider the space-time location, but t now is x0, right? Is a coordinate. So better to think of the space-time location of a moving particle as describing a curve in space-time. This curve has a name. This is called the word line. And the standard way of doing that is to condense all the space into one dimensions. So this will be in the x, and the time would be in the horizontal dimension, ct. And the curve will be this. Now, written like that, when we have photons, which curves they will take on this space-time?
Diagonal, like x
Exactly
equals
45 degrees, exactly. So a photon could go like that. This will be photons. And of course, if you're taking it as a cone, this is called a light cone. Right? This is the light cone. So if I sit down and do nothing, right, my world line is not going to be fixed because time is always progressing. So my world line will just go like that. If I'm moving, then it will go something like that, right? I can move back and forth in various directions. right? But note that being a massive, meaning I cannot travel faster than light, I cannot cross the light cone. I am always inside the light cone, right? Because I cannot go, for example, right? I cannot go from here to here. Why not?
You can travel faster than light.
Because going from this location in space-time to that location requires me to go faster than light, which I cannot. Okay, so this is not allowed.
If I said something can do it, is it a space like object?
I'm not sure that I fully understand the question. We do not know of any physical particle that can travel faster than light. There are theories. You might have heard, objects like tachyons, which are thought of as being able to. We don't have any evidence that such particles actually exist in nature. But you can envision various particles that do various things. Okay, we don't know of any, since this is a course in physics, there are no known physical particles that travel faster than light. In fact, there are no known massive particles that travel at the speed of light. A massive particle can travel close to the speed of light, but it can never reach the speed of light. So if I want to describe the motion of a particle, right? Let's say again, I'm here. I want to describe the motion of a particle in this space-time, right? Then I need to give the 4 coordinates of the particle, right, as a function of, again, some parameter along this word line. So again, I take this word line, I cut it into pieces, and I define some parameter. Let's call it sigma, whatever. Then in order to define where I am, where an object is, right, I need to define the location of a particle. Right, I write down x mu, all 4 coordinates, x mu as a function of this parameter, which I call sigma. Now I can choose many such parameters, but there is one natural choice of such parameter, which is what?
Proper time.
Proper time, of course. That's really only parameter that we discussed so far, right? Again, sigma just describes where I am on the curve. Again, think of it like I'm going now to hike the Israel Trail, right? And I tell you in advance, this is my path that I'm going to take. So at a given, time, or at a given time is not a good, I specify the location along this path, right? I say, right, I'm at point number 1 is here along the path. Point number 2 is here. Number 3 is here. Number 4 is here, whatever. Right? So I can select various parameters, but of course the only natural parameter I have is the proper time. Natural parameter, the only one. Proper time, tau. I hear that there is an alarm here indicating that there might be an alarm shortly. I don't know if you got it. Did any of you got a notification that there might be an
Yes.
Okay, so can you continue on, or shall we take now a break?
Yes, but I need to leave, but I'm in Miluim, so like they make us go somewhere now.
No. Okay, so we take a break now, and we resume back in 10 minutes after the alarm, so something like 15 minutes from now, and we'll compensate for that down the line. So I'm leaving the Zoom open,
Thank you.
and we return back after the 10 minutes after the alarm. All right, so see you in 15 minutes.
I'm back as well. I just can't turn on my camera because of where I am.
How many people are here? I'm waiting like a few more minutes until people come up, and whoever can open the camera will open the camera. Okay, those who managed to come back, please open your camera so that I could see that you're here. Is everyone okay? I'll give it one more minute so that everybody come back. Yeah, I didn't consider that we might have to add up some lecture because of all the lost time, but now let's do what we can with the next, I don't know, 15 to 20 minutes. All right, everybody's okay? Okay, so let's resume back. So we're talking about a way of describing where we are in space-time. And we said that there is this thing which is called a world line, specifying our location. And in order to know where we are, we need to find a parameter that tells along the world line. So, we can choose any parameter, but the only natural parameter that there is tau, is the proper time. So normally we write down where we are as x mu, all of our four components, as a function of the proper time. Right? This will specify where are we. Okay? In 4 dimensions, of course. Given that, now we can, this is our location. So if this is our location, my location, okay, each one has its own unique world line. If this is my location, what would be my velocity, my 4 velocity? How would I define it?
The width of tau, the power time.
Exactly. There's only one thing which is naturally to do, which is just taking the x mu and divide it and take the differential with respect to tau. So that's how I'm going to find the 4 velocity. U mu is defined as dx mu over d tau, which is again pretty much the only natural thing I can do, right? And again, like any vector, u mu, the forward velocity, is defined at a given point. Okay. D tau, reminder, we define it using d tau squared is a 1 minus 1 over c squared eta mu nu delta x mu delta x mu. Which, if you want, d tau is square root of dt squared minus dx squared over c squared. So dt square root of 1 minus dx over dt squared over c squared, which is dt square root 1 minus beta squared, right? Beta v over c. So using that, and using the definition of the forward velocity, right? U0, what is x0? What is x0? Zero component of the location.
Isn't x0 time?
CT, right? Well, I define it using C, so it's d CT over square root of 1 minus beta squared dt. Just C over square root of 1 minus beta squared. So it's gamma C. Again, I mean, C is going to be given to 1 sooner, but right now I still keep it just to make sure that you see that I'm fully self-consistent with what I'm doing. Right? UI, actually it's a capital U normally. So UI is dxi over square root of 1 minus beta squared dt. So 1 over square root of 1 minus beta squared dxi over dt, which is gamma vi or gamma beta I c. Again, I mean, most textbooks at this point, you find that there is no c anymore. I still keep it just because I know it's confusing and I don't want to confuse you more than needed. Okay, what's the norm of the forward velocity? Right. Norm, I can write u mu, or eta mu nu, u mu u nu. Right, eta mu nu, dx mu over d tau, dx nu over d tau, which I'm going to write down in a completely irresponsible way. Eta mu nu dx mu dx nu over d tau squared. Completely illegal, but it gives the right result, right? Eta mu nu dx nu is just d tau squared, so I get c squared minus. So the forward velocity has a constant norm.
Yeah, we did this in particles too.
Yeah.
This is also true for curved spacetime.
You'll see.
Is there a significant?
Yes, norm. The fact that the norm is a scalar, yes, scalar is a scalar. It changes. It's not varying. Yeah.
Is there a significance for c squared being negative? Like, does it have any?
C squared is not negative. It's a minus c squared. Yes, the norm of v is negative.
Does it have any physical implications?
It does have a physical implication. If we go back here, right? My world line or my four velocity. What type of vector is it? We said there are three types of vectors. Remember? Or you need me to remind you. We said three types of vectors.
It's contravariant, no?
No, that's not what I meant. Any vector is contravariant. We have three types of vectors, right?
Mm-hmm.
What type of vector is the four velocity?
Supposed to be space-like, no?
No. Well, we just proved the norm is
Timeline.
negative.
Covector?
No, it's a
That's
vector.
timeline.
Has
Isn't
an
it?
upper index, so it's
It's a
contravariant.
It's a contravariant vector, which is shortly a vector. It is a vector. It's tangent to a curve, which is my location. I asked what type of vector. We said there are three types of vectors.
Light-like. We just
What?
showed its norm is c², right?
Timeline. Time.
It's a time-like vector, right? The norm is negative. It's a time-like vector, right? It has a negative norm. What does it mean? Now you ask me, now was a question in physics. So what does it mean? So first, it's a time-like. By the definition I have here, it's a time-like. It's a negative norm. What does it mean that it's a time-like? It's actually plotted right here. That means that it's obliged to stay within the light cone. If it was a light, what was the velocity of light?
You mean C?
Right. So what type of vector is the velocity vector of a light?
Light-like.
Light-like. That means what? Physically, that it's obliged to move on the light cone. Right? And if I had a space-like vector, that means that I could move away outside of the light cone. That's the meaning of a space-light vector. Velocity. Traveling faster than light. Now I can't do that, right? Any massive particle cannot do that. Right? And so I am obliged, the norm of my four velocity is always negative. I'm light-like, and physically that means that I'm obliged to stay within the light cone. I cannot travel faster than the photon. All right, guys. Can be a little bit confusing at the beginning, but it makes perfect sense. And again, if you think of it for a second, there is nothing really else that I can do here. Once I made all these definitions, I'm very much strict to go exactly in this path. I can't do anything else. For example, now after I define the velocity, how can I define the acceleration?
Differentiate.
Exactly, right? So the forward acceleration A mu is going to be defined as du mu over d tau. Know that it's common to use capital U here. You'll see why we're using capital U. So this is a forward acceleration. And again, there's nothing else you can do here. What will be the force? Relativistic full force. F mu. Just M A mu. So just M du mu over d tau. That's really the relativistic version of Newton's second law of motion. What's written here, right? This is what replaces Newton's second law of motion. Now, of course, it gets everything we need, right? It reduces to the Newton's law in the familiar, non-relativistic limit, inertial frame. satisfies the principle of relativity. If there is no force, then of course du mu over the tau is equal to 0. So Newton's first law holds. Of course, the constant that we added here, m, right now we're treating it as a constant. What is that?
Resonance.
Yeah, it's called the particle's rest mass. Now, mathematically and quite interestingly, the forward acceleration is always perpendicular to the forward velocity. A mu u mu is eta mu nu du mu over d tau u nu. I can write it down as 1/2 d eta mu nu u mu u nu over d tau. This is constant, so it's 1/2 d minus c squared over d tau, which is 0. So the forward acceleration is always perpendicular to the forward velocity. But you shouldn't really be worried about that, because what it really tells is that there are only 3 independent equations of motion. The fourth one depends on the other 3. So there's nothing really that changes from what you're familiar with. Only a more general concept.
Why is it always perpendicular? It reminds me of circular motion, where the acceleration is always perpendicular to velocity.
In a way, yes, but it's now the fourth component, the dependent component, is the time component. So you have to think of it. It's not, you don't have any simple analogy. So you have again, so you have the 3 accelerations that you have are independent, but then the fourth one, the one that closes that, would be dependent, but this will give you the time. So you don't have. I don't really have a way of visualizing that easily.
Okay.
Okay. Then the next is to define the energy and momentum of massive particles. So obviously, how am I going to define the forward momentum? Again, so far, right, we defined 2 new vectors, right? The 4 vector velocity, 4 vector acceleration. Actually, 3 vectors and 4 vector force. 4 force, right? So everything now kind of follows quite easily. So how am I going to define the forward momentum?
MV mu.
What?
MV mu.
Exactly, right? There's nothing I can really do here except writing down P mu is m dx mu over d tau, or m u mu. That's all. So what's the norm of the forward momentum? P squared. P mu. Right, well, we have the norm of the velocity, which is minus c squared. So the norm of the momentum is minus m squared c squared. Right? And then what is the zeroth component? P0. Well, we had the zeroth component of the velocity, right? It was gamma c. So the zeroth component of the momentum is just gamma mc. And what's the ith component of the momentum? Pi. Gamma beta I mc, which is gamma m vi. Now, if I take the limit where v is much smaller than c, then beta, what about it, is much smaller than 1, right? It's v over c. What about gamma? What is gamma in this limit?
approach
It
is
goes to
1.
1.
What?
It goes to 1.
Well, let's go. What the next? What is the next component in the Taylor
Plus
expansion?
V divided by C.
Right? Plus
V
Guys,
divided by
no.
half V divided by C.
Half beta squared. Guys, are you all familiar with the Taylor expansion? I don't like the quietness.
Yes, we're familiar.
Yes.
Check out why this is true, right? This is the next term in Taylor expansion. So in that case, what is pi in this limit? It's just going to be mvi. Then the extra term would be vi cubed, so I throw it away. What is p0? Well, gamma is 1, right? So it's a gamma mc. So it's mc plus 1/2 m v squared over c. So this is, of course, the Newtonian momentum. What is that? P0?
The energy.
Energy.
Doesn't look like an energy. What do I need to do to make it an energy?
Multiply by C.
Multiply by c, right? So c p0 is mc squared plus 1/2 mv squared plus O of v to the 4. What is this term?
Kinetic energy.
Right, EK. What is this term?
Relativistic.
What?
The rest energy.
This is the rest mass energy, right? Which Einstein got just out of the equation, right? You don't need to do anything. You just get it out of the equation. This is the rest mass energy. Right, so this is the E equal mc squared, right? If a particle is at rest mass, that's what you get. So this is why the for momentum, it also has another name, which is called the energy momentum 4 vector. And one last thing before we call it a day, right? We can write down using that two terms here. So we have from here P0 is E over C, right? Which we can write as actually from here. This is just Pi squared plus M squared C squared to the power 1/2. Which again, you're familiar with this equation, right? We get it directly from here. Right? So basically we derived,
Can I ask a question?
yes.
What's the point of writing it like that? Like, why is that a relevant notation?
I'm not sure to understand the question. What do you mean, why is that a relevant notation?
Like, what? I mean, I just not really understand. Like, you could see that from the equation. So why? Is there something extra here that we're trying to see, or just a representation of what P0 is?
Well, you're familiar with this equation, I guess, no? You've seen this equation your first year. I'm just showing it to you that you get it right here from what we did. I mean, if the question is about the general denotation, you'll see it's impossible to do it any other way. When we start bending spaces, which we actually plan to give you some introduction to that on Sunday, then you'll see exactly It's absolutely essential. There is no other way of doing that I'm aware of. If you're asking about that specific equation, that specific equation is something which you've seen in the first year. But now I think, or I hope, right, you get a full feeling of where it comes from and where does it stand in the big picture.
Okay, thank you.
All right, guys. So it's been a bit awkward. You had to go in the middle, but now we're out of time. So have a safe and quiet weekend, and I'll see you on Sunday, the usual time, 10 a.m. for an compensating one lecture of the lectures we're going to lose in the future. And I do ask you again, those of you who have or planning to take repeated exams, please send me an email telling me when is your repeated exam. So we'll see when we can schedule additional lectures. I don't want to start running into like 3-4 lectures a week because it might be too much. So I prefer to use the times that we can now that is not too crowded. Of course, it's always a little bit less good to have that, but it's easier to do it now. Also, of course, it's easier to do it when we are now at the beginning of the semester, not when we're close to the end of the semester and everybody gets stressed from the exams, etc. All right. Have a safe day and
Thank you.
enjoyable weekend as much as we all
Yeah,
can.
bye-bye.
And I'll see you on Sunday then. I'll send an email notification. See you.
Thank you.
Bye.
Bye.
Thank you.